Early 1943. A quiet Luftwaffe airfield somewhere inside, occupied Europe, sat under a cold gray sky, as a group of German engineers slowly walked around a massive American bomber parked near the edge of the runway. The aircraft had not arrived there by design. It had landed after a damaged mission, forced down by mechanical trouble, and intercepted before it could escape. Now the bomber stood surrounded by curious technicians, wearing heavy coats and carrying clipboards, now studying the machine from every angle. One of the engineers stopped beneath the long wing and looked up toward the four large engines mounted along its span. The aircraft was enormous compared to most fighters, and even larger than many bombers the Luftwaffe regularly encountered. Its tall landing gear, narrow fuselage, and wide wings gave it an unusual appearance that immediately caught the attention of the inspection team. The aircraft was a consolidated B-24 Liberator, one of the newest heavy bombers the Americans had begun sending across Europe. German intelligence officers had already heard reports about the bomber's range and payload, but seeing the aircraft up close was something different. Engineers walked along the fuselage examining panels and structural joints, while others climbed inside the open bomb bay to inspect the internal frame. One officer tapped on the aluminum skin with his knuckles and commented on how thin it felt compared to some German aircraft designs. Another pointed out the long wing that stretched far beyond the fuselage, its narrow shape unlike anything seen on most European bombers. The team was not particularly alarmed by what they saw at first. German engineers had studied captured aircraft before, and the procedure was familiar. The goal was always the same: understand the enemy's technology, identify weaknesses, and determine whether any useful ideas could be copied or improved upon. At first glance, the B-24 looked like a capable bomber, but not a revolutionary one. It carried 4 engines, defensive guns, and a large bomb load, features shared by many heavy bombers already flying in the war. But as the engineers continued their inspection, something about the aircraft began to stand out in ways they had not expected. It wasn't the engines or the weapons that drew their attention, that it was the way the bomber had been built. One engineer studying the internal structure noticed that many sections of the aircraft appeared to be assembled from flat, simple panels joined together in straight lines, rather than the complex curves often used in German aircraft construction. Components seemed designed to be installed quickly and replaced easily. Bolts, brackets, and structural supports were arranged in ways that suggested the aircraft had been designed not only to fly, but to be built repeatedly on an assembly line. Another engineer examining the bomb bay structure noticed something else. Many of the parts looked standardized, almost interchangeable with components found elsewhere in the aircraft. Instead of handcrafted fittings carefully shaped for a single airframe, the bomber appeared to use parts that could be produced in large quantities and installed wherever they were needed. The deeper the team looked, the more that pattern appeared. The aircraft was not simply a machine built for combat performance. It was a machine designed to be manufactured thousands of times. That realization slowly changed the tone of the inspection. Engineers began discussing how quickly such an aircraft could be assembled in a factory environment. Now, one officer studying the structure reportedly remarked that the Americans seemed less interested in perfect craftsmanship than in building aircraft that could be produced rapidly and repaired easily. At that moment, the captured bomber began representing something larger than a single aircraft design. It represented an industrial approach to warfare that German engineers had not fully encountered before. Over the next year, intelligence reports would reveal just how serious that discovery was. Because the bomber sitting quietly on that airfield was only one example of a machine that American factories were producing in staggering numbers. And for the German engineers studying the aircraft that day, the most troubling realization was still ahead of them. The bomber itself was dangerous, but the factories capable of building thousands of them were far more dangerous. For German engineers and intelligence officers during World War II, A captured enemy aircraft was far more than a damaged machine sitting on a runway. It was an opportunity. Throughout the war, the Luftwaffe maintained specialized technical units tasked with studying Allied aircraft whenever one could be recovered intact or nearly intact. These teams included engineers, mechanics, and experienced test pilots who carefully examined every component of the captured machine. Their goal was simple: understand how the enemy built its aircraft, identify weaknesses, and learn whether any design features could be adapted or improved for German use. When Allied aircraft were forced down due to damage, mechanical failure, or navigation mistakes, German recovery teams moved quickly to secure the wreckage before it could be destroyed by its crew. The aircraft would then be transported to a technical evaluation center where engineers could study it in detail. This process had already provided valuable insights earlier in the war. German specialists had examined several Allied fighters and bombers, learning about radar equipment, defensive armament arrangements, and engine technologies. Sometimes the aircraft were even repaired and flown again by German test pilots. These test flights allowed the Luftwaffe to measure performance characteristics, such as speed, climb rate, and maneuverability, while also giving pilots a chance to experience the aircraft from the inside. In many cases, the captured machines were repainted with German markings and used in training exercises, so that Luftwaffe pilots could practice fighting against aircraft similar to those used by their enemies. By the time the B-24 Liberator arrived on that German airfield in 1943, the engineers examining it were following a well-established routine. They expected to find a bomber built according to principles already familiar to them: strong structure, powerful engines, and defensive gun positions designed to protect the aircraft during bombing missions. Germany itself possessed one of the most advanced aircraft industries in the world at the start of the war. Companies such as Messerschmitt, Junkers, and Focke-Wulf had produced some of the most capable military aircraft of the era. German engineers were proud of their work, and their aircraft designs often emphasized precision engineering and high-performance characteristics. Fighters like the Bf-109 and Fw-190 were built to achieve maximum speed and maneuverability, while bombers such as the Ju-88 combined versatility with strong construction. German aircraft manufacturing often relied on skilled labor and complex engineering solutions intended to maximize the performance of each individual aircraft. That philosophy shaped the way German engineers approached the examination of captured machines. When they inspected the B-24 Liberator, they expected to see the same kind of engineering priorities they understood so well: structures carefully shaped for aerodynamic efficiency, components individually crafted for specific airframes, and design decisions focused primarily on flight performance. But the longer they examined the American bomber, the more they began to realize that it had been built with a different set of priorities. The B-24 did not appear to emphasize elegance or complex craftsmanship in the same way many German aircraft did. Instead, its structure seemed designed for something else entirely. Panels were arranged in straight sections that looked easy to assemble. Components appeared standardized in ways that suggested they could be produced quickly in large quantities. Even the internal structure of the aircraft seemed organized in a way that would allow multiple sections to be built separately before being joined together during final assembly. For the German engineers studying the bomber, these details raised an unsettling question. If the aircraft had been designed this way deliberately, then the Americans might not simply be building aircraft for performance. They might be building them for mass production. And that possibility hinted at a problem far larger than the single bomber sitting on the airfield in front of them. As German engineers continued examining the captured consolidated B-24 Liberator, the bomber began revealing a design philosophy very different from what they were used to seeing in German aircraft. At first glance, the B-24 looked unconventional. Its fuselage was tall and narrow, almost slab-sided compared to the smoother, more curved bodies of many European bombers. The wings stretched outward with a long, thin profile that seemed unusually slender for such a large aircraft. Inside the bomb bay and fuselage sections, the structure appeared surprisingly simple. Instead of complex curves and intricate metal shaping, many components were built from straight aluminum panels, connected by riveted frames and reinforcing beams. Engineers inspecting the bomber quickly realized that this simplicity was not the result of poor craftsmanship. It was deliberate. Each section of the aircraft appeared designed to be assembled quickly, using standardized parts. The structural ribs followed repetitive patterns. Panels could be attached using identical fasteners across large areas of the airframe. Even wiring and hydraulic lines were arranged in predictable layouts that mechanics could install or replace without extensive custom fitting. To engineers trained in a system that often prioritized finely tuned performance, the B-24 seemed almost industrial in its construction. It looked less like a handcrafted aircraft and more like a machine designed to move efficiently along a factory assembly line. One of the most striking features was the bomber's long wing, based on the Davis airfoil design. This wing allowed the aircraft to achieve excellent range and lift while maintaining relatively efficient performance at high altitude. The wing structure also followed the same philosophy seen throughout the rest of the bomber: straight structural elements, the large uniform panels, and components that could be assembled in predictable sequences during production. The aircraft was clearly capable in combat, but it was also clearly designed with manufacturing in mind. The more the engineers studied the bomber, the more they began to realize that its true strength might not lie in any single technical feature. Instead, its advantage came from the way all those features supported rapid construction. The B-24's fuselage could be divided into multiple sections that different factory teams could assemble simultaneously. Wings, engines, landing gear, and internal components could all be prepared separately before being brought together during final assembly. This modular approach meant that production could continue even if one section of the aircraft experienced delays, because other sections were still being built at the same time. German engineers were familiar with aircraft designed for high performance, but many of those designs required complex manufacturing processes and highly skilled labor. The B-24 appeared to follow the opposite approach. Its design reduced the need for specialized craftsmanship by relying on standardized components that could be produced in large quantities. If a panel was damaged, it could be replaced with another identical panel from the factory. If a mechanical component failed, the mechanics could install a replacement part without reshaping or modifying it to fit. These details suggested that the aircraft had been created not only to perform bombing missions, but also to be manufactured repeatedly with minimal variation. That realization began to change the way the German engineers viewed the bomber sitting on their airfield. The B-24 was not simply an American answer to existing German bombers. It was a machine built to take advantage of a massive industrial system capable of producing aircraft on a scale far beyond what many nations could sustain. And if that industrial system truly existed, then the bomber in front of them might represent only a tiny fraction of what American factories were capable of delivering to the battlefield. By the summer of 1944, the Allied armies advancing through France faced a logistical crisis that could have easily stopped their momentum. After the landings in Normandy in June, Allied forces fought a brutal campaign to break through German defensive lines surrounding the beachhead. When that breakthrough finally came in late July during Operation Cobra, the situation changed almost overnight. The American armored divisions suddenly surged out of the narrow Normandy front and began racing across the French countryside. German defenses, weakened by weeks of fighting and constant air attacks, began collapsing in several sectors. Entire German formations were forced to retreat quickly to avoid being surrounded. For Allied commanders, the rapid advance was both an opportunity and a problem. Their forces were moving faster than anyone had expected, and the further they moved from the Normandy beaches, the longer the supply lines became. Every mile the front moved forward meant another mile that fuel, ammunition, spare parts, and food had to travel to reach the troops fighting at the front. Normally, railroads would have taken over much of that transportation burden. But in France, the rail network had been heavily damaged by Allied bombing before the invasion. Bridges had been destroyed, rail yards shattered, and large sections of track rendered unusable. German forces retreating across the countryside also sabotaged infrastructure wherever they could, further slowing any attempt to repair the railways. As a result, Allied supply planners suddenly faced a dangerous situation. Their armies were advancing rapidly, but the traditional supply routes that should have supported those advances simply did not exist. The German commanders watching the Allied breakout believed this problem would stop the advance sooner or later. They expected that American armored units would eventually run out of fuel and ammunition once their supply lines stretched too far beyond the Normandy beaches. Instead of slowing down, however, the Allied supply system adapted in a way that surprised German intelligence officers observing the battlefield. In August 1944, Allied commanders launched one of the largest truck-based supply operations of the war. It became known as the Red Ball Express. The system worked by dedicating entire road networks exclusively to military truck convoys, transporting supplies from depots near the Normandy beaches to the rapidly advancing front lines. Thousands of trucks began moving along these routes day and night, carrying everything from fuel and artillery shells to rations and spare parts. Drivers operated in continuous shifts, often driving for hours without stopping except to refuel or repair damaged vehicles. The convoys rarely paused because the entire system depended on constant movement. Trucks traveling toward the front delivered their cargo and then returned along separate routes to collect another load. Roads across northern France soon filled with long columns of American transport vehicles, kicking up clouds of dust as they moved supplies forward at a relentless pace. German reconnaissance teams observing these routes reported seeing convoys that stretched for miles, sometimes appearing as an endless stream of trucks rolling across the countryside. What the German commanders had expected to become a logistical breakdown instead became a massive demonstration of Allied mobility. Even though railways were unusable and the front lines were advancing rapidly, the truck convoys continued feeding fuel and ammunition to the units pushing eastward. The very system German officers had mocked for wasting gasoline was now proving capable of sustaining one of the fastest advances of the European campaign. The Allied armies had not outrun their supplies after the Normandy breakout. Instead, thousands of trucks were racing to keep up with them. Among the German personnel studying the captured consolidated B-24 Liberator was a structural engineer whose job was to analyze the aircraft's internal construction in detail. While test pilots focused on performance and flight characteristics, engineers like him spent hours examining the hidden parts of the aircraft that most people never noticed. He climbed inside the bomber's fuselage with a flashlight and a notebook, moving slowly through the narrow interior passages that ran from the cockpit toward the tail. The interior structure of the aircraft revealed its true design philosophy more clearly than the exterior ever could. The engineer studied the metal frames that supported the fuselage and the riveted panels that formed its outer skin. Instead of complicated curved sections that required skilled craftsmen to shape each component individually, many of the structural parts followed simple geometric patterns. Straight beams connected to uniform ribs, and large sections of the fuselage appeared to be assembled from repeating pieces that could be manufactured in identical batches. As he examined the bomber's wiring and hydraulic systems, he noticed something else. The cables, pipes, and mechanical components were arranged with unusual clarity and accessibility. Panels could be removed easily, allowing mechanics to reach important parts without dismantling large portions of the aircraft. Even the bomb bay doors and mounting structures appeared designed with maintenance in mind. The engineer had spent years working on German aircraft structures, where many components were carefully crafted for maximum aerodynamic efficiency or performance. In contrast, the American bomber looked almost utilitarian in its design. Every part seemed organized around a simple principle: make the aircraft easy to build and easy to repair. As he continued studying the bomber, the engineer began writing detailed notes about the production implications of what he was seeing. The structure of the B-24 suggested that its designers had intentionally simplified many aspects of the aircraft in order to speed up manufacturing. Instead of relying heavily on specialized craftsmanship, the aircraft appeared designed so that multiple sections could be assembled independently and then joined together during final construction. Wings, fuselage sections, tail assemblies, and internal systems could all be built in parallel on separate production lines. Once completed, those sections could be transported to a final assembly point, where workers would connect them into a complete aircraft. The engineer realized that this approach would allow factories to produce large numbers of bombers simultaneously, rather than building them one at a time from the ground up. Even small details supported this idea. The rivets used throughout the structure followed standardized patterns, meaning workers could install them quickly without needing custom measurements for each airframe. Many mechanical components appeared interchangeable between different aircraft, allowing damaged parts to be replaced without complex adjustments. For a production system focused on efficiency and speed, these features would be extremely valuable. The engineer understood that the bomber in front of him was not simply the product of a single factory workshop. It was the result of a manufacturing philosophy designed for large-scale industrial output. If American factories were capable of building aircraft this way, then producing hundreds or even thousands of identical bombers might be possible. That realization slowly transformed the captured aircraft from a technical curiosity into something far more troubling. The bomber itself was impressive, but the system that created it might be even more dangerous. As German engineers continued studying the captured consolidated B-24 Liberator, they began comparing its design philosophy with the way aircraft were normally built in Germany. German aircraft engineering before and during the war had focused heavily on maximizing performance through precision design. Aircraft companies invested enormous effort into refining aerodynamics, strengthening structures, and improving engine performance so that each aircraft could achieve the highest possible speed, all climb rate, or maneuverability. Engineers working for companies such as Messerschmitt, Junkers, and Focke-Wulf often treated aircraft construction almost like a specialized craft. Individual components were carefully shaped and fitted to each airframe, and many designs required highly skilled labor to produce correctly. This approach produced some of the most advanced aircraft of the early war years, including fast fighters and versatile bombers that could outperform many of their opponents. However, it also meant that building those aircraft required significant time, specialized tools, and experienced workers. When engineers began comparing those methods with what they saw inside the B-24 Liberator, the difference in philosophy became increasingly obvious. The American bomber did not appear to sacrifice its performance completely, but its design clearly emphasized something else: the ability to be manufactured quickly and repeatedly across multiple factories. And this difference represented a deeper shift in how the United States approached wartime production. Instead of focusing solely on building the most technically refined aircraft possible, American designers had prioritized standardization and scalability. The goal was not simply to create a powerful bomber, but to create a bomber that could be produced in enormous numbers without requiring constant redesign or specialized craftsmanship. This meant designing aircraft structures that could be divided into manageable sections, produced simultaneously, and assembled efficiently on large factory floors. It also meant ensuring that parts were interchangeable, so that repairs could be completed quickly using standardized components. For German engineers accustomed to aircraft production that relied heavily on precision craftsmanship, this approach was both fascinating and unsettling. The B-24 seemed to represent a manufacturing system capable of producing bombers on a scale far beyond what Germany's aircraft industry was accustomed to achieving. Even if German engineers could match or exceed certain technical aspects of the bomber, the Americans might still possess an advantage if they could simply produce far more aircraft. As reports from Allied bombing raids continued arriving across Europe, that possibility became increasingly difficult to ignore. Every time German cities or industrial targets were attacked, new waves of bombers appeared in the skies. For the engineers studying the captured B-24, the aircraft had become more than a technical specimen. It was evidence of a different way of thinking about industrial warfare, one where victory might depend not only on engineering excellence, but on the ability to produce machines faster than the enemy could destroy them. As German engineers continued analyzing the captured consolidated B-24 Liberator, intelligence reports arriving from across Europe began confirming what the structure of the aircraft had already suggested. The bomber was not being built in small numbers. It was being produced on a scale that few German planners had imagined possible when the war began. American factories were operating at a pace that transformed aircraft manufacturing into something resembling a massive industrial assembly operation, rather than a traditional aircraft workshop. Instead of relying on a single factory, carefully building aircraft one at a time, the United States had organized production so that multiple factories could manufacture the same bomber simultaneously. Different companies produced separate sections of the aircraft: wings, fuselage components, engines, all landing gear and internal systems, while final assembly plants brought all those pieces together into complete bombers ready for combat. This approach allowed production to continue, even if one facility slowed down, because other factories were still manufacturing the remaining components. The system resembled the large automobile assembly lines that American industry had perfected before the war. Though one of the most remarkable examples of this approach was the massive bomber production plant operated by Ford Motor Company at Willow Run in the United States. This factory had originally been known for producing automobiles, but during the war, it was converted into a facility capable of assembling heavy bombers on an industrial scale. The plant stretched across enormous factory floors where workers and machines moved aircraft components along assembly lines designed for continuous production. Instead of building a single aircraft from start to finish in one location, the Willow Run system allowed partially completed bombers to move through different stages of assembly, while workers installed engines, wings, wiring, and other components in a carefully organized sequence. The results of this system soon became visible in the skies over Europe. By 1944, the B-24 Liberator had become one of the most widely produced heavy bombers of the war. The thousands of aircraft were rolling off production lines across the United States and being shipped overseas to join Allied air forces operating against Germany. For German planners who studied aircraft production statistics, the numbers were startling. The United States was producing bombers faster than many countries could replace their combat losses. Even if German fighters managed to destroy a number of bombers during a raid, new aircraft were constantly arriving to take their place. The captured bomber sitting on the airfield represented only one example of a machine that American factories could replicate over and over again. For engineers who had spent years designing aircraft with careful craftsmanship and precision manufacturing, the scale of this production system was difficult to ignore. German industry had produced advanced aircraft designs throughout the war, but its factories faced limitations in resources, labor, and production capacity. The American system appeared to operate on an entirely different level, combining standardized design with vast industrial resources to create a steady flow of bombers entering the conflict. Each new B-24 delivered to the battlefield increased the pressure on German defenses and added to the growing fleets of Allied aircraft flying missions over Europe. The bomber that German engineers had once inspected as a captured curiosity was now being reproduced in numbers that suggested something far larger than a single aircraft program. It represented the industrial power of a nation capable of turning factory output into an overwhelming strategic advantage. By 1944, the conclusions that German engineers had begun forming while examining the captured consolidated B-24 Liberator were becoming impossible to ignore. Intelligence reports arriving from different sectors of the war painted the same picture again and again. Allied bomber formations were growing larger, not smaller. German fighter units that intercepted these raids often reported seeing dozens or even hundreds of bombers approaching their targets in tightly organized formations. Even when Luftwaffe fighters managed to shoot down some of the aircraft, the overall number of bombers appearing in the skies seemed to remain steady. From the perspective of German defense planners, this pattern raised an alarming question. If German fighters were destroying bombers during raids, why did the Allied bomber fleets not appear to shrink? The answer gradually became clear as production data and reconnaissance reports reached German command structures. The United States was not merely replacing lost aircraft. It was producing them at a rate that allowed entire bomber groups to expand while still covering combat losses. For the engineers who had studied the B-24's construction, this information confirmed their earlier suspicions. The aircraft's design made sense only when viewed as part of a large industrial system capable of building thousands of identical machines. Every structural feature they had observed, standardized panels, modular sections, and interchangeable parts, supported a production strategy designed for speed and scale. The bomber had not been engineered simply to perform well in combat. It had been engineered so that factories could build it quickly and repeatedly with minimal variation between airframes. This approach allowed American industry to maintain a constant flow of new bombers into the war. For German planners facing the growing pressure of Allied bombing campaigns, this realization carried serious implications. Strategic bombing raids were already placing enormous strain on German industry and infrastructure. Factories producing aircraft, vehicles, and weapons were frequent targets for Allied bombers flying deep into German territory. Rail yards, fuel depots, and industrial centers were attacked repeatedly in an effort to weaken the German war economy. Each time a formation of B-24 bombers crossed the skies over Europe, it represented not just a single group of aircraft, but the output of a massive industrial machine operating thousands of miles away. German engineers and analysts began to understand that even if their defenses managed to destroy some of these bombers, the factories producing them could simply replace those losses with new aircraft arriving months later. This meant that the Allied bombing campaign possessed a kind of momentum that was difficult to stop once it began. The captured bomber, examined months earlier, had revealed the manufacturing philosophy behind this strategy. But the true scale of that system was only now becoming clear. German engineers had expected to study a powerful enemy aircraft. Instead, they had discovered evidence of an industrial capability that threatened to overwhelm their own production capacity. The bomber, sitting quietly on that airfield, had been only one machine, but it represented a production system capable of filling the skies with many more. And for those responsible for defending German industry, that realization suggested a future where stopping the bombers might become increasingly difficult as their numbers continued to grow. By the final years of the war, the implications of what German engineers had discovered while examining the captured consolidated B-24 Liberator were becoming visible across the entire European battlefield. The bomber itself was not the fastest aircraft in the sky, nor was it the most maneuverable, but it possessed something that made it extremely dangerous in a prolonged conflict. It could be built in enormous numbers. As American factories continued producing aircraft at a relentless pace, the new bomber groups arrived in Europe month after month. These aircraft joined large formations, flying missions against industrial centers, transportation networks, and military infrastructure across German-controlled territory. Each raid represented not just the bombers visible in the sky that day, but the industrial system capable of replacing them if they were lost. German air defenses fought fiercely against these bombing campaigns. The fighter pilots scrambled to intercept the incoming formations. Anti-aircraft batteries fired thousands of shells into the sky, and engineers worked constantly to repair damaged factories and rail lines after each attack. Yet the pressure continued to grow as Allied bomber forces increased in size and frequency. For German planners trying to defend their country's industrial capacity, the situation revealed a fundamental problem. The even successful interceptions that destroyed several bombers could not permanently reduce the overall strength of the Allied bombing force. New aircraft were constantly arriving to reinforce the bomber groups already operating in Europe. The captured bomber that engineers had studied earlier in the war had demonstrated exactly why this was happening. Its design made large-scale production possible, allowing factories to produce bombers far more quickly than traditional manufacturing methods would have allowed. In the broader context of the war, the B-24 Liberator represented more than a powerful aircraft. It symbolized the industrial capacity behind the Allied war effort. American factories had transformed their production lines to build aircraft, vehicles, and weapons at a scale unmatched by most nations involved in the conflict. The same assembly line principles that once produced automobiles were now producing heavy bombers capable of flying thousands of miles and delivering massive bomb loads against enemy targets. German engineers, who first inspected the captured bomber, had focused on its structure, studying its panels and internal frames to understand how it had been built. What they eventually realized was that the aircraft's greatest strength did not come from any single engineering innovation. Instead, it came from the system that produced it. The B-24 was a bomber designed not just for performance, but for replication. Thousands of identical aircraft could roll out of factories using standardized parts and modular construction methods. That capability ensured that the Allied air forces would never depend on a single aircraft surviving each mission. If one bomber was lost, another could replace it. When German engineers admitted they had never seen production organized in quite this way before, they were recognizing something fundamental about modern industrial warfare. In a conflict where factories determined how many weapons could reach the battlefield, the nation capable of producing machines faster than the enemy could destroy them possessed a powerful advantage. And the captured bomber sitting on that airfield had revealed exactly how that advantage was being built. The captured B-24 showed German engineers more than just a bomber. It revealed a production system capable of building thousands of them. And in modern war, the side that can build faster often wins the sky.